All right, so let's get started. Recall that we're talking about LP spaces. So what have we done last time? Well, last time we defined LP spaces and stated some properties of LP spaces. So suppose you have omega f mu, which is a sigma finite measure space. And suppose I have a function f taking omega to r bar, which is fb of r bar measurable. Remember that R bar is the extended real line. So it's the closed interval minus infinity, infinity. I'm defining this symbol. It looks like a norm, but yet right now I don't yet know that it's a norm. So I'm defining this symbol, symbol f sub p to be absolute value of f to the p, integrate that, and then take the pth root of that. I'm defining this left-hand side to be the pth root of the integral of mod f to the p d mu, if 1 less than or equal to p less than infinity. And I'm defining this symbol, norm f infinity, to be the infimum of k greater than 0, such that mod f of omega is less than k mu almost everywhere. We discussed last time that these two quantities are always well defined for any function you may take in this family. It may be infinite. Then if the quantity is finite, then you say that the function belongs to LP. So for any 1 less than or equal to p less than or equal to infinity, we define LP of omega f mu to be the set of all functions f taking omega to r bar such that f is measurable, and this symbol norm f sub p is less than infinity. All right. Then what did we do? Then we convinced ourselves that for any 1 less than or equal to p less than or equal to infinity, LP of omega f mu is a vector space. We did that. Now the next question that comes up is, this symbol which looks like a norm, is it actually a norm? The answer is yes. But to do that, we have to do a bit of work. So what are some of the things we did? First thing we said is that, remember that if the norm of f is 0, you cannot conclude that f is 0 everywhere. You can only conclude that f is 0 mu almost everywhere. So the way you get around this is you think in terms of equivalence classes. You say, I will consider two functions equivalent if they agree, except on a set of measure 0. In other words, if the function which is always 0 and the function which is 0 almost everywhere are considered the same thing. So if you do that, then you have some chance of making this thing a norm. And then we had Young's inequality. This I claim was an entirely calculus result. We left the proof. The proof was given here. This just had to do with maxima, minima, basic properties of calculus. Then we had Holder's inequality. So Holder's inequality, well, okay, then we also introduced this notation. Suppose P and Q belong to the closed interval 1 infinity. We'll say that P and Q are conjugate exponents if 1 over P plus 1 over Q is 1. Okay, so you should remember what conjugate exponents means, because it makes it easier for me to say things. If I just say P, Q are conjugate exponents, I don't have to keep telling you, oh, 1 over P plus 1 over Q is 1. Okay, so basically Holder's inequality says, suppose I have P, Q in the closed interval 1 infinity, which are conjugate exponents, and one of them is in LP and the other one is in LQ, then the product has to be in L1. And the L1 norm of the product has to be less than or equal to the LP norm of the LP function times the LQ norm of the LQ function. That was Holder's inequality. This we did last time. We first looked at the case when P is 1, Q is infinity, and we proved it. Of course, the case when P is infinity, Q is 1 is similar. It's just that the roles of F and G have been flipped. Then we looked at the case when P, Q belong to the open interval 1 infinity, and then we proved this. Here is where we used Young's inequality. Okay, so we're done with Holder's inequality, and now we come to Minkowski's inequality. And basically, Minkowski's inequality is going to help us conclude that the thing we are thinking is a norm is in fact a norm. Okay, so let's see what this says. So here is the theorem. This is Minkowski's inequality. So for P in the closed interval 1 infinity, and for Fg belonging to LP of omega f mu, we have norm f plus g in LP less than or equal to norm f in LP plus norm g in LP. Now I am saying norm, but I don't yet know it's a norm. Okay. Now, of course, remember that since f and g belong to LP, f plus g belongs to LP, because we have already shown that LP is a vector space. So if f and g belong to LP, then f plus g will belong to LP. So let's see how you prove this. Okay, so the proof, the case P equals infinity is not difficult. I'll leave it to you to fill in the details yourself, okay? So I'll leave this as a DIY, do it yourself, okay? And so now let's look at the case when P is less than infinity. So assume P is in the interval closed at 1, open at infinity. Note that there are no two conjugate exponents here, okay? There's only one exponent P. There's no Q, there's just P. All right, so now I claim that the result is clearly true if the P norm of F plus G is 0. Okay, why is that? Well, suppose the P norm of F plus G is 0, then the left side of this inequality is 0. The right side is non-negative, so of course it's true. Okay, so if norm F plus G in P is 0, in other words, the left side is 0, then this inequality is automatically true. Note that the right-hand side is non-negative. So what we'll do is, we'll assume that this symbol is greater than 0. All right. Okay, so now what I'm going to do is the following. Now let me look at norm F plus G, P to the P. Okay, so this is the LP norm to the pth power. So this is just going to be the integral absolute value of F plus G to the P d mu. Why is this true? This is just true by definition. Right? By definition, the LP norm is the pth root of this guy. So the LP norm to the pth power is just the integral of this guy. Okay. And then of course I can write this as the integral absolute value of F plus G times absolute value of F plus G to the P minus 1 d mu. Why can I do this? Well, this is just basic stuff you learn in algebra. Okay, then what I'll do is the following. Then I will take this absolute value of F plus G and I'll write it as less than or equal to absolute value of F plus absolute value of G. That's what I'm going to do. So I'll get norm, what's the left-hand side? Norm F plus G, LP norm to the pth power, which equals this quantity. You guys with me so far? This is going to be less than or equal to the integral absolute value of F times absolute value of F plus G to the P minus 1 plus absolute value of G times absolute value of F plus G to the P minus 1 d mu. Any questions with that? All I've done is I've taken this absolute value of F plus G and I've upper bounded it by absolute value of F plus absolute value of G. And so I'll get absolute value of F times this guy, which is over here. We get absolute value of G times this guy, which is over here. Okay. So now I'm going to make a claim. Okay. So let P, Q be conjugate exponents. All right. So actually what I'll do is I'll look at the case when P is in 1 infinity. So suppose P is in 1 infinity and let P and Q be conjugate exponents. Right, so you know what that means. That means that 1 over P plus 1 over Q equals 1. Well, this implies 1 over Q is 1 minus 1 over P. So this is going to be P minus 1 over P. And so you get that the conjugate exponent of P is Q equals P over P minus 1. Do you guys agree with that? If I take P, then the conjugate, again, I'm taking P in the open interval 1 infinity, then the conjugate exponent Q is P over P minus 1. All right. Okay. So now I claim the following. This guy, absolute value of F, this is an LP. We already know that. I claim that this guy is an LQ. All right. Similarly, this absolute value of G, this is an LP already. I claim that this guy, same guy, is an LQ. So we claim that absolute value of F plus G to the P minus 1 is an LQ. Because remember, if this is the case, then you can use Holder's inequality. Right? I'm taking a product of absolute value of F times absolute value of F plus G to the P minus 1. The first guy is an LP. If the second guy is an LQ, then the product is an L1 and I can use Holder's inequality. So that's where I'm going with this. So we claim that absolute value of F plus G to the P minus 1 is an LQ. Let's check this. Indeed, if I take absolute value of F plus G to the P minus 1 and I take its qth power, what am I going to get? This is going to be the integral absolute value of F plus G to the P minus 1. And now remember what Q is. Q is P over P minus 1. And so again, now you use your laws of exponents. So this is going to give you the integral absolute value of F plus G. Now I'm going to have this P minus 1 will cancel. So I'll just be left with to the power P. And this is finite. Right? This is finite. Why is that? This is since F plus G is an LP. So F plus G to the P minus 1 is indeed an LQ. Any questions with that? Okay. All right. Okay, so what do we have now? So thus, absolute value of F plus G to the P minus 1. This is an LQ. Now, let me rewrite the equation that I had on the previous slide. Okay. Now recall. And this is what we had on the previous page. Recall that this is true. Now I'll use Holder's inequality and I will say that this guy is an LP. This guy is an LQ. So its product is an L1. And the integral of this product is less than or equal to the LP norm of this times the LQ norm of that. Similarly, this guy is an LP, this guy is an LQ, the product is an L1. So now, by Holder's inequality, what do we get? We get norm F plus G, the LP norm to the pth power is going to be less than or equal to. Actually, let's just break it up into one more step. Right, you're adding these two integrals, and then you will say that the first guy, this guy is going to be less than or equal to norm F in LP and norm F plus G to the P minus 1, this norm in LQ. Do you guys agree with that? This is just Holder's inequality. This term, okay, let me highlight it. The highlighted term is an LP. The highlighted term in yellow. The term highlighted in green is an LQ. So the product is an L1. And the integral of the product is less than or equal to the LP norm of the yellow function times the LQ norm of the green function. Okay. And actually, maybe I should just mention this is LQ. Similarly, this term, this is going to be less than or equal to the LP norm of G, and then I'm going to take absolute value of F plus G to the P minus 1, and I'm going to take the LQ norm of that. I have a question for you guys. What's the relation between these two quantities? The LP norm of F and the LP norm of absolute value of F? What's the relation? Are they different? What's that?
Same.
They're exactly the same. Yes, they're exactly the same. To take LP norm, you first take absolute value, then you take the peak power. So of course, these are exactly the same. Anyway, that's just in case you were wondering how you got norm F to the P. I'm using the fact that the LP norm of mod F is the same as the LP norm of F, assuming of course F is in LP. Okay, so then let's just get rid of this. Okay, and okay, I need one more page. All right, so now what do I have? So if I Holder's inequality, what do I get? I get norm F plus G, LP norm to the pth power is less than or equal to the LP norm of F times, I'll use different colors here so that it's easier to see. I take mod F plus G to the P minus 1, and then I take its LQ norm. Right, and then I'll have plus norm G Q, and then I'll take mod F plus G to the P minus 1, and then I'll take its LQ norm. Any questions so far? Questions? All right, so now let's see what this quantity is. Okay, so let me highlight this quantity. Oh, it's the same as this quantity. All right, so let's see what this highlighted quantity is. 1 second, just no, it's quite. Was that in response to the question, whether there were any questions? Somebody typed no in the chat box.
Yes, sir.
Okay, okay. All right, so now let's see what this quantity is. All right, so now let's look at mod F plus G to the P minus 1, and then let's look at its Q norm. Right, so what do? So you're going to take mod F plus G to the P minus 1. You're taking the Q norm, so you should take this to the Qth power. Then you should integrate it. And then you should take the Qth root. Do you guys agree with that? That's just the definition. So this is going to be what? So inside, I'm going to have integral mod F plus G to the Q times P minus 1 d mu all to the 1 over Q. And now you remind yourself of something. You say Q times P minus 1 is just P. Okay. This just follows from P and Q being conjugate exponents. So this is just P. All right, so you're going to get the integral mod F plus G to the P d mu all to the power 1 over Q. Right? And so you say, okay, this is integral mod F plus G to the P. Sometimes I may not write the measure d mu because there's only one measure in town. So you always know which measure I'm using for integration. And then I'll look at this 1 over Q. Okay, I need to find out what that is. So I'll say 1 over Q is P minus 1 over P. So now I'm going to get P minus 1 over P. And then again, integral absolute value of F plus G to the P to the power 1 over P to the power P minus 1. Everyone agree with that? Now the thing inside the red brackets, this is just the norm F plus G, the LP norm of F plus G. Do you guys agree with that? So what do I get? I get basically, I get the LP norm of F plus G to the P minus first power. Agree? Now I will go back into this equation. I will plug this particular result into that equation. So plugging into star, we get, but what is the left side? The left side is norm F plus G in LP to the pth power less than or equal to. Then I have this P norm of F. And now there is this quantity, the Q norm of F plus G to the P minus 1. We just found out what it is. It is this quantity right here. So I'll get norm F plus G. This is the LP norm to the P minus first power. Plus, and again, now here this is the LQ norm of G, so that's fine. And then this quantity, again, is this thing. So I'm going to get norm F plus G in LP to the P minus 1. And you can see where this is going, right? So basically what I have on the right side is norm F LP plus norm G LP times norm F plus G P minus 1. Any questions with this? Okay, so let me just rewrite what I have. The left side is norm F plus G to the pth power. So norm F plus G to the pth power. And remember, this is the LP norm, less than or equal to. On the right side, you have norm F plus norm G, norm F plus norm G. And then you have norm F plus G to the P minus 1. Okay, so now you know what you should do. You should just divide by norm F plus G to the P minus 1. On the left side, you have that quantity to the pth power and dividing by that quantity to the P minus first power. So I will get norm F plus G in LP less than or equal to norm F in LP plus norm G in LP. Okay, any questions with this? Questions?
Sir?
Yes.
Sir, can you go to the previous slide?
Okay.
Sir, in the last equation, you have written that norm of F, pth norm of F plus pth norm of G.
Correct.
But in the previous equation, it is after the plus sign, it is qth norm of G. Is it
Ah,
right?
very good, very good. Thank you.
And in the first line also a star equation of star, that there is also with qth norm of G.
Sure. Thank you. There are some mistakes here. Okay, so let's fix them one by one. This is P norm of F, Q norm of this guy. That okay. All right, so F is an LP, this guy is an LQ. So P norm of F, Q norm of this guy, that's correct. G is an LP, this is an LQ. So P norm of G, Q norm of this guy, that is also correct. Then P norm of F, Q norm of this guy, that is fine. Here, this should be P, correct?
Yes, sir.
Okay, so I have P norm of F, Q norm of this guy, P norm of G, Q norm of this guy. Okay, then let's see where the other mistakes are. Norm F plus G to the P less than or equal to the P norm of F. Now the Q norm of this guy we have computed to be P norm of F plus G to the P minus 1. So P norm of F plus G to the P minus 1 plus, okay, now this is a mistake. This is, I've written Q norm of G. This is not correct. This should be P norm of G, right? So P norm of G, P norm of G, then Q norm of this guy, but Q norm of this guy is P norm of this guy to the P minus 1. So P norm of this guy to the P minus 1. Now, yes, now I can take P norm of this guy to the P minus 1. I can pull that out, take it common, and then I'll have P norm of F plus P norm of G. Correct now?
Yes, yes, sir.
Okay, thank you. Thank you very much. And so now we get on the left side P norm of F plus G to the P norm of F plus G to the P less than or equal to P norm F plus P norm G, P norm F plus P norm G times P norm of F plus G to the P minus 1, P norm F plus G to the P minus 1. Now I divide by the P norm of F plus G to the P minus 1. So I get P norm of F plus G less than or equal to norm F plus 1 G. Okay, I think now it's correct. Thank you very much. So far, so good? Okay. All right. So then just one last loose end. Okay, by the way, here we're dividing by this. And this is why we had to first set aside the case when the P norm of F plus G was 0. If you remember, initially we said first, we said clearly the result is true if P norm of F plus G is 0. So we're assuming that P norm of F plus G is greater than 0. That's why we can divide by that. Okay. All right, so this is what we get. Now the only, the one hole that's left is we have to consider the case when P is 1 and therefore Q is infinity. So finally consider the case when, oh, there is no Q here. I'm sorry, I keep saying Q. There is no Q, there's only P. Or let me put it this way, in the statement there is no Q, in the proof there is a Q. Okay, consider the case when P equals 1. Okay, so in this case, I'll have norm of F plus G 1. So this is going to be the integral absolute value of F plus G. Now I'll say inside the integral, I'll use the triangle inequality. So I'll have absolute value of F plus absolute value of G. And now I'm adding two non-negative functions and integrating. This is less than or equal to the sum of the integrals. But hey, this is exactly the result we want. So this is norm F, the one norm of F plus the one norm of G. Okay, so here you get it straight away without having to do any other fancy work. Any questions? Okay, so what have we shown? We have shown that for any P in the interval 1 to infinity, 1 included, infinity excluded, P norm of F plus G is less than or equal to P norm of F plus P norm of G. In other words, we have shown that for any P in 1 infinity, 1 included, infinity excluded, this norm symbol satisfies the triangle inequality. Yes? So far, so good? The one thing I'm leaving for you to fill in is the case P equals infinity. So now let's see what we have. I claim that we are now ready to say that this thing that we have been saying looks like a norm is actually a norm. Okay, so let's let's consider this. So consider LP of omega F mu equipped with this symbol. Okay. This is this norm symbol. Now we will prove that it is a norm. So what do you need for norm? The first thing you need is that this thing applied to any function should be non-negative. That is true. Clearly, the P norm of F is greater than or equal to 0. No problem there. And the other thing is you want the P norm of F is 0 if and only if F is 0 mu almost everywhere. So this is fine because the requirement is that the norm of a vector should be 0 if and only if it's the 0 vector. But because we are identifying functions which are equal almost everywhere, the function which is 0 almost everywhere, this is your 0 vector. Okay. The 0 vector is not the function which is 0 everywhere. It is all functions which are 0 almost everywhere. Okay, and this is okay since we are identifying functions which are equal almost everywhere. So we say that if there are two functions which agree almost everywhere, we'll say they're the same function. In other words, if some function is 0 almost everywhere, we'll say, oh, this is no different from just being 0. All right, so the first property of a norm is satisfied. The second property required of a norm is that for any scalar alpha, the P norm of alpha F should be mod alpha times P norm of F. This is a very simple thing. I'm going to leave it for you to check. And the third property is the triangle inequality. So finally, by Minkowski's inequality, if Fg belong to LP and P is in 1 infinity, then the P norm of F plus G less than or equal to P norm of F plus P norm of G. So what you get out of this is that this symbol is indeed a norm on LP of omega F mu. Any questions? Any questions with what we're saying? But now remember that in doing this, we have taken some equivalence relations. Put another way, we have decided that if two functions are equal almost everywhere, we're going to say it's the same function. So now this thing is in fact a vector space. This thing is in fact a norm. Okay, so by the way, this symbol is the LP norm or the P norm. Now we can say safely that it is a norm. Remember when you study functional analysis, you have a vector space V. If you have this symbol, which is a norm, then you say that this pair is a normed vector space. Okay. So here what we're saying is LP of omega F mu together with this symbol is a normed vector space. All right, now the next question you can ask is this normed vector space complete? Namely, does every Cauchy sequence converge? Okay, so actually what I want to do is I want to perhaps duplicate. Okay, that is good. So let me come to the first one. And then let me erase this out. Okay. And now I have another copy of the page, so I can safely do that. Okay. So now let me just remind you of a couple of things. So now the next question you can ask is the space LP of omega F mu complete? So thus LP of omega F mu together with this symbol is a normed vector space. Okay, so now the next question that comes up is this vector space complete? So what does it mean for a vector space to be complete? Well, a vector space, a normed vector space is complete if every Cauchy sequence converges. The reason I'm doing this is I just want to remind you of what we mean by a Cauchy sequence, what we mean by a convergent sequence. Okay, so this is just a recall. Okay. The definitions I'm stating are for any normed vector space. I'm going to state them in particular for this space. So the sequence Fn, n going from 1 to infinity, taken from LP, I'm just going to write LP. I'm just going to write LP since there is only one measure space we're playing with, right? So instead of writing LP of omega F mu, I'll just write LP. So the sequence f and n going from 1 to infinity from LP is said to be Cauchy. So if for any epsilon, well, actually, let me put it this way. If limit as m n go to infinity, norm of fn minus fm goes to 0. Let's now say this more precisely. So what you're saying is sequence is Cauchy is as you go further along the sequence, the terms of the sequence get close to each other. That does not necessarily mean that they converge to some limit. All they're saying is that the terms are getting close to each other. Okay, so let's see this. If limit n goes to infinity, p norm of fn minus fm equals 0. So what does this mean? I.e., given epsilon greater than 0, there exists some natural number capital N, which is big enough, such that whenever small n and small m are greater than or equal to capital N, we have a norm of fn minus fm is less than epsilon. So that's what it means for a sequence to be Cauchy. You're familiar with that. Let's say what it means for a sequence to be convergent. So the sequence fn, n going from 1 to infinity in LP, is said to converge to f in LP if limit n goes to infinity, norm fn minus f in LP is 0. Put another way, i.e., given epsilon greater than 0, there exists n in n such that whenever n greater than or equal to capital N, we have norm fn minus f in LP less than epsilon. Okay, so that's what we mean by a sequence being convergent. So in this case, the sequence fn, n going from 1 to infinity, is said to be convergent. All right, so now you know that in any metric space, in any space where you have a notion of distance, you can talk about Cauchy sequences, you can talk about convergent sequences. You say the metric space is complete if every Cauchy sequence converges. Now, if you have not seen metric spaces, that's okay, because here we're working in a normed vector space. And in a normed vector space, we know what it means for a sequence to be Cauchy. We know what it means for a sequence to be convergent. And if I have a normed vector space in which every Cauchy sequence is convergent, then I will say that that normed vector space is complete, and I will call it a Banach space. Right? Okay. And now again, this was a repeat from earlier, so I'll just erase this. Actually, maybe this part I'll keep. Okay, so let's go over this. So LP of omega F mu together with this symbol is a normed vector space. Okay, we did that. It turns out that this space is complete. So what does that mean? Complete means every Cauchy sequence converges, i.e. whenever we have a Cauchy sequence Fn n going from 1 to infinity in LP, one can find an F in LP such that norm Fn minus F in LP goes to 0. In other words, Fn converges to F in LP. Okay. All right, any questions so far? Questions? All right. Now, everything we've said automatically carries over to probability spaces because, of course, probability spaces are special cases of measure spaces. So let's see what would happen there. Only thing that changes is the notation. So if omega FP is a probability space, then the foregoing LP spaces facts and notions apply. Okay. Only thing that may change is the notation may be a bit different. Okay, so for 1 less than or equal to p less than infinity, if we have a random variable x, which is a measurable function, defined on omega fp, we will say that it belongs to LP of omega fp if expectation mod x to the p is less than infinity. And of course, this makes perfect sense because remember what this quantity is. This quantity is just the integral mod x to the p dt. Okay. And of course, in this case, the p norm of x is expectation mod x to the pth power, the whole thing pth root. Right. So of course, all these things carry over directly to probability spaces. Okay, because probability spaces are just measure spaces with total measure 1. Any questions? All right. So the last couple of things I want to do is I want to just convince you that these LP omega f mu, these are actually complete. All right. So now I think in the interest of time, maybe I will just, as I said, I have some notes written up and periodically I erase it and write it out deliberately because then that ends up slowing things down a little bit. But now I think I'm just going to go ahead with whatever is written here. Okay. So suppose omega f mu is a sigma finite measure space. Okay. Suppose P is in the closed interval 1 infinity. All right, we know what LP of omega f mu is. And we have shown that LP of omega f mu together with this symbol is a normed vector space. All right, now we want to show that this normed vector space is in fact complete. In other words, we want to show that every Cauchy sequence converges. Now, for that, we will find a certain theorem useful. And to state that theorem, we need to also recall a certain definition. The definition we want to recall is one of absolute convergence. So let's recall this. So suppose I have V together with a norm. Okay, so let V with this norm be a normed vector space. Let's first remind ourselves what it means for a series to converge. Okay, so suppose I have the sequence xn, n going from 1 to infinity, taken from this vector space V. And let's say I look at this infinite series, some xn, n going from 1 to infinity. I will say that this infinite series converges to some element x in V if the sequence of partial sums converges to x. This is exactly what you did on the real line, right? So I will say that this infinite series, some xn, n going from 1 to infinity converges to x in V if the sequence of partial sums converges to x. In other words, the partial sum is some n going from 1 to capital N xn. So this is the nth partial sum. If this thing converges to x, then I'll say that this infinite series converges to x. Okay, let's just make a note as to what this is. This is the capital Nth partial sum. Okay, so this is what I mean by a series converging in a normed vector space. By the way, of course, what this means is if I say sum n going from 1 to infinity, xn converges to x as n goes to infinity, what that means is if I look at the norm of sum n going from 1 to capital N xn minus x, then this norm goes to 0 as n goes to infinity. All right, so that's what it means for a series to be convergent. What does it mean for a series to be absolutely convergent? Well, the series, the infinite series, sum n going from 1 to infinity xn is said to be absolutely convergent if whenever I first take the norms of all the xn's and then add them all up, that is also finite. Okay, so note that this is a series, this is an infinite series where I'm adding an infinite number of vectors. This is a series of what? Is it a series of vectors? No, it's a series of numbers, right? Because each norm xn is a non-negative number. Right? Okay, so I'll say that the series sum n going from 1 to infinity xn is absolutely convergent if the sum n going from 1 to infinity norm of xn is less than infinity. Okay, that means if somebody gives me an infinite series here, if I, for each of these guys, I take its norm and then I add them all up and I still get something finite, then I will say that this series is absolutely convergent. You guys with me? Okay. Now, here is a result. Suppose, so now you can ask about the relation between convergence and absolute convergence. So what is the relation between convergence and absolute convergence? Which one implies which?
Absolute convergence implies convergence.
Right, absolute convergence implies convergence, always. That is that, that's for free. Absolute convergence implies convergence. But one of the facts is that if you're in a complete normed vector space, then convergence and absolute convergence are exactly identical. Okay, so that's what we're saying here. So if I have a normed vector space V together with this norm, this is complete if and only if every absolutely convergent series in V is convergent. Okay. You guys with me? So this, by the way, did you guys do this in functional analysis? Many of you are in measure theory and functional analysis, right? Did you do this?
Yes, sir.
What?
Yes, sir.
You have done this in measure theory and functional analysis? Dinesh, have you done this in measure theory and functional analysis?
Yes, sir.
Okay. So a normed vector space is complete if and only if every absolutely convergent series in V is convergent. Okay, so you have seen it in functional analysis, that is good. I am not going to test you on the proof of this. Okay, so I'm not going to ask you to prove this. I've kind of left it out. It's in my, it's in some other notes. If you are really keen and want me to share these notes, let me know. But as I said, I'm not going to test you on the proof of this. We're just going to use it. That is all. Okay. So basically, we're saying that a normed vector space is complete if and only if every absolutely convergent series is convergent. In other words, if we want to show that LP is complete, we should show that every absolutely convergent series is convergent. You guys with me? All right. So here's what I'm going to do. I'm going to just do the proof for P less than infinity. Okay. So suppose 1 less than or equal to P less than infinity. Okay. So I'm saying that for 1 less than or equal to P less than infinity, the normed vector space LP of omega F mu together with this norm is complete. It also is true for P equals infinity. It's still true. I'm not going over the proof of that. Also true for P equals infinity, but I'm not going to go over the proof of that. All right, so if you believe this result, and I believe it, then what you need to do is you just need to show, it suffices to show that every absolutely convergent series in LP is convergent. Are you guys with me? So how should we do this? We should take an arbitrary series, assume it's absolutely convergent, prove that if it's absolutely convergent, then it must be convergent. Okay. We want to show that every absolutely convergent series is convergent. So we take an arbitrary absolutely convergent series, show that it must be convergent. So we'll say, suppose I have a sequence fk, k going from 1 to infinity contained in LP, such that the corresponding series, sum k going from 1 to infinity fk, is absolutely convergent. So what does that mean? If I take norm fk and I add up from k going from 1 to infinity, I get something finite. Okay. So suppose I have a sequence fk, k going from 1 to infinity in LP, such that the series k going from sum k going from 1 to infinity fk is absolutely convergent. What does that mean? That means that sum k going from 1 to infinity, norm fk is finite. Now, what do we want to do? We want to show that the sum k going from 1 to infinity fk is in fact convergent in LP. Right? So we want to show that there exists some capital F in LP such that the sum k going from 1 to infinity fk converges to f. So what does that mean? That means the sequence of partial sums for this guy converges to capital F. So what that means is that if I look at the nth partial sum k going from 1 to capital N fk, and I subtract capital F and I take the p norm, then this should go to 0 as capital N goes to infinity. You guys with me? This, remember, is just the nth partial sum. Okay, so here's how we'll do this. So let B be the sum k going from 1 to infinity norm fk. Now this is finite. Why is this finite? Vijay, why is this finite? Vijay, are you there?
Yes, sir.
Why is this finite? B is sum k going from 1 to infinity norm fk. I claim this is finite. Why is this finite?
fk is convergent.
What's that?
Convergent. Fk is summation k equal 1 to infinity. Fk is convergent.
No, that's what you're trying to show. You want to show that this is.
Sir,
We have
FK
assumed that
is
it
lies in
absolutely
LP.
convergent. Sir, we have assumed that it is absolutely convergent.
Exactly. That is just the assumption. That is the basic
Yeah.
assumption. The assumption is that sum k going from 1 to infinity norm fk is finite. So why is this true? This is true by assumption. We are assuming that fk is a sequence such that this is true. So it was a simple question. If that's it. This is just the hypothesis that this is convergent. Okay, now I'll do the following. Let Gn be the sum k going from 1 to n absolute value of fk. Why is this function well defined? It's a finite sum of non-negative measurable functions. That is well defined. Now let G be the sum k going from 1 to infinity absolute value of fk. Why is this meaningful? Answer is there on the screen. Right? It's a sum of non-negative measurable functions. When we were doing integration, we saw that if you're dealing with non-negative functions, very important, non-negative, integral of the sum is the sum of the integrals, right? And when you're adding an infinite number of non-negative functions, nothing bad will happen. Worst case scenario, you'll get infinity, but you'll never have infinity minus infinity. So that's what I mean, that this G is meaningful. Worst case scenario, it is infinity, but I will never get infinity minus infinity. So G equals sum k going from 1 to infinity mod fk is meaningful because it is a sum of non-negative measurable functions. Do you guys agree with that? This is just stuff from real analysis. Okay, this is just measure theory. Okay, now I claim that Gn increases to G. Can somebody tell me why? Anita, why does Gn increase to G? The questions I'm asking are much simpler than you realize. Why does Gn increase to G?
Sir, Gn is from K1 to N. If we take limit n tend to infinity, it will be Z.
Why is that? Basically, what I'm saying is by definition,
Yes,
G,
sir.
by definition, G is the limit as n goes to infinity of Gn. So why does
Yes,
Gn increase to G? Well, that is how the infinite sum G is defined in the first place, right? If you fix, these are functions. So if you fix any point in omega, G evaluated at omega is defined to be the limit of this guy evaluated at omega. So that's why Gn increases to G pointwise. Okay, so let me just probably make a note. So for each omega in omega, by definition, G of omega is limit is going to be right. This is limit n goes to infinity, sum k going from 1 to n, absolute value of f k of omega, but this guy is just Gn. That's how we have it. So for each omega, G omega is the limit of Gn omega. And why is the increasing part there? I've talked about the conversions. Why is the increasing part there? I have a non-negative series, right? The more terms I add, the series can only get bigger. It cannot get smaller. All right. All right. So here now, what am I going to do is the following. The P norm of Gn is going to be, well, what is Gn? Gn is sum k going from 1 to n mod fk. Okay, so Gn is sum k going from 1 to n mod fk. So the P norm of Gn is the P norm of sum k going from 1 to n mod fk. This is less than or equal to sum k going from 1 to n P norm of mod fk. Why is this true? You're on mute.
By Minkowski's inequality
What's that?
that we proved. Minkowski's inequality we proved earlier.
Oh, yeah, but maybe you can, right, that is true. In general, the triangle inequality, that's what you're saying. Right, yeah, Minkowski's inequality, you can say that. You can extend that to n functions. So I have P norm of Gn is the P norm of sum k going from 1 through n mod fk. Then by the triangle inequality, which is Minkowski's inequality in LP spaces, you get less than or equal to sum k going from 1 to n P norm of mod fk. Now we went over this. What is the relation between norm f and norm absolute value of f? They are the same thing. So norm of absolute value of fk is just norm fk. So I have this as sum k going from 1 to n norm fk. Now remember that this is here every term is non-negative, right? So if I add more terms, the result cannot get smaller. So this C is less than or equal to sum k going from 1 to infinity norm fk. But wait, by assumption, this guy was just b, which is finite. All right, so what have we shown? We have shown that if I take mod Gn to the pth power, integrate it, and then take the pth root, that's going to be less than or equal to b. So what you get is integral mod Gn to the pth power is less than or equal to b to the p, right? So here I'm just taking the pth power on both sides. Now what I'll do is I'll use, so now let's keep these following facts in mind. Gn and g are non-negative measurable functions, and Gn increases to g, right? If Gn increases to g, what can you say about Gn to the p and g to the p? What can you say about Gn to the p and g to the p? Gn to the p is going to increase to g to the p, right? Because Gn increases to g, so Gn to the p increases to g to the p. So Gn, g are non-negative measurable functions. Gn increases to g, so Gn to the p increases to g to the p. So let's just make a note here. Gn increases to g, so Gn to the p increases to g to the p. Now remember, we're dealing with non-negative measurable functions here. So Integral g to the p is limit n goes to infinity integral gn to the p. Now remember, for any n, integral mod gn to the p is less than or equal to b to the p. So integral g to the p d mu, which is limit n goes to infinity integral gn to the p d mu. This is by the monotone convergence theorem, right? This is by monotone convergence theorem. And now you look at the thing inside the integral, and that is no more than b to the p. So this is less than or equal to b to the p less than infinity. So what does this mean? This means that g is an LP, right? Okay, now if G is an LP, that means G has to be finite almost everywhere. Because we have studied this thing. Suppose I take the integral of a non-negative function and I get something finite, then the function has to be finite almost everywhere. So G is an LP. Now what is G? G, remember, is this guy. If G is an LP, it must be finite almost everywhere. So the sum k going from 1 to infinity mod fk converges almost everywhere. All right. So the sum k going from 1 to infinity fk converges almost everywhere. Can somebody tell me why? Someone tell me why this is true. Why is this true?
So FK are positive.
FK, you don't know if FK are positive. No, you just know that the mod FK are non-negative. So suppose
Then
that,
we use absolutely convergent series imply convergent.
Convergent.
correct, where?
Yes.
Where are you using that? That is the correct answer, but where are you using that? In which space? In which space are you using that? You're using that in the real line, right?
Yeah.
Because suppose I have an omega, okay? So basically, so suppose sum k going from 1 to infinity, absolute value of fk of omega is finite. Okay, I have fixed an omega here, okay? I have fixed an omega. Now this is just a series of real numbers, right? So this is basically, now I'm using the fact that the real numbers are complete. So on the real line, every absolutely convergent series is convergent. So this implies that the sum k going from 1 to infinity, fk of omega is finite. Let me, rather than saying it's finite, let me say converges. And why is this true? Because as soon as you fix an omega, you're talking about a series of real numbers. Does that make sense? So you're using absolute convergence implies convergence for real series. Right? So you're saying, so this thing converges almost everywhere. So take an omega where this guy converges. Well, then for that omega, this guy has to converge because of the completeness of real numbers. Okay. All right, now remember that part of our job here was to identify a limit, right? So here's how we can identify a limit. So we know sum k going from 1 to infinity mod fk converges almost everywhere. So by completeness of the real line, sum k going from 1 to infinity fk converges almost everywhere. That means this object is well defined, right? So and now this is our natural candidate for the limit. So let capital F be the sum k going from 1 to infinity fk. All right, now I claim that mod f is less than or equal to g, right? Why is that? Because if I take mod f, that is going to be mod of this, and this is going to be less than or equal to sum k going from 1 to infinity mod fk, which is g. So, now remember, g is an LP. So f is an LP, right? So f is dominated by g. G is an LP, so f has to be an LP. Okay, so f is an LP. So now we have got a function in LP, which could be the limit of the sequence of partial sums. Now we want to show that the sequence of partial sums actually converges to it, right? Now note that the sum k going from 1 through n fk converges to f mu almost everywhere. Let me ask you, काम हो गया क्या कि और कुछ करना है? I have already shown that this series converges to F, right? Now what is there to do? क्या बचा है? Vijay, what's left? Dinesh, what's left? Dhiren? I have to show there are different senses in which convergence can happen, right? Yes, this converges to F almost everywhere, but I want to show that it converges to F in LP. That is still left. So I cannot just stop here and say, oh, काम हो गया. No, काम नहीं हो गया. Because right now I just know that some K going from 1 through an Fk converges to capital F almost everywhere. What I want to do is I want to show that it converges to F in LP. So we want to show that some K going from 1 through an Fk converges to capital F in LP. That is, we want to show that the norm of some K going from 1 through an Fk minus F, the LP norm goes to 0. If I want to show that the norm of Xn goes to 0, it is good enough to show that the norm of Xn to the pth power goes to 0. Right? The two statements are equivalent. So we'll show that the pth power of the norm, some K going from 1 through an Fk minus F goes to 0. You guys with me? Now let's prove that this quantity goes to 0. So we know that some K going from 1 through an Fk minus capital F goes to 0 mu almost everywhere. This we had. So now we want to use dominated convergence theorem, right? Because we're going to say this thing goes to 0 almost everywhere. Maybe if dominated convergence theorem applies, then limit of the integral is integral of the limit. So now let's look at this quantity to the pth power. So I'll take mod F minus some K going from 1 through an Fk, take the pth power. Now I'll use the triangle inequality, right? So mod A minus B is less than or equal to mod A plus mod B. So then I get less than or equal to mod F plus some K going from 1 through mod F plus absolute value some K going from 1 through an Fk to the pth power. This is less than or equal to mod F plus some K going from 1 through n mod Fk. So here what I've done is I've used triangle inequality. Absolute value if the sum is less than or equal to sum of absolute values. And then I'll say wait, this mod F is less than or equal to G. That is already done. And here I'm taking some K going from 1 through n mod Fk. This is a series of non-negative numbers. So if this is going to be dominated by the corresponding infinite series, some K going from 1 to infinity mod Fk. And this is also G. In other words, this function is dominated by 2g to the power p. Now remember, g is in LP. So 2g to the p is in L1. So this guy goes to 0. Okay. This thing is dominated by an integrable function. So by the Lebesgue dominated convergence theorem, integral mod F minus some K going from 1 through an Fk to the pth power goes to 0. But what does that mean? That basically means that some K going from 1 to infinity Fk converges to F in LP. Any questions to this? Questions? Yes.
Can you go to the previous slide?
Okay.
So here we have shown in the second last line, and above that we have shown show F belongs to Fp, and also we are showing that sum over K equals to 1 to an Fk converges to F almost mu almost everywhere.
Correct.
And also we have shown that F belongs to LP. Then why again we have to show that this series is converges in LP?
Because to show that it converges in LPs, you have to show that if I take this minus this and I take the pth power and I integrate, that will also go to 0.
Oh, okay.
Right? Unfortunately, I don't have an example for you now where I wish I had an example right now, but the point is, you know that almost everywhere this guy converges to F, that you know. That means if I take this minus this and I take absolute value, that will go to 0 almost everywhere. Okay, that's fine. If I take that to the pth power, that'll also go to 0 almost everywhere. That's fine. But now I want to show that the integral of that goes to 0. Right? Because I want to show that this guy converges to f in LP. Remember that when we talked about different senses in which functions can converge, a convergence almost everywhere on a probability space implies convergence in measure. Convergence in LP implies convergence in measure. But the relation between convergence almost everywhere and convergence in LP is somewhat subtle. You cannot just say if one holds, the other holds. Does that make sense?
Yeah.
So maybe one way to say it is if I have a sequence Fn convergent to F almost everywhere, and the functions are all in L1, there's no guarantee that Fn will converge to F in L1.
Okay.
So that's basically what's going on. Does that answer your question?
Yes, sir. Yes.
Okay, so the
And also, sir,
yeah,
we have also means for complete a real line, we know that absolute convergence implies to the convergent of series.
correct.
But here we are going to prove that absolute convergence implies convergence. Does it? I mean, for proving the our space is complete, we need to prove for all the spaces. We need to prove that absolute convergence implies convergence.
Right. See, the thing is, where is the action happening? This statement is happening on the real line. So basically, this statement is saying for a series of real numbers, absolute convergence implies convergence. What we're trying to show here is that for a series of functions, absolute convergence implies convergence.
Okay.
Right? And remember, when you're talking about the series of functions, the norm is not just taken pointwise, the norm is taken in some clever way using integrals and all that. So I agree with you that at a point, if you fix a point, yeah, absolute convergence implies convergence. Yes. But here what you're trying to show is that absolute convergence implies convergence in the space of functions. Does that answer your question?
Yes, sir. Yeah.
Any other questions? All right. By the way, have any of you not filled out? Let's stop recording here. Stop recording. Stop cloud recording.